Sometimes you can, if you wish, you can keep one blank slide. वो भी कर सकते हो, इसके लिए मैंने पूछा.
ओके ओके, ब्लैंक स्लाइड भी कर सकते हैं. ओके ओके, इंसर्ट करके इधर इधर इंसर्ट करके.
हाँ, एक ब्लैंक चाहे तो अभी भी वो डाल देगा एक स्लाइड.
हाँ हाँ,
जरूरत पड़े तो
करेक्ट करेक्ट.
और आप बना के लाने का.
So shall I start? So very good evening to all. So today we are going to discuss some very interesting aspects on solid state NMR. Very interesting aspect, because I will be discussing more on NMR spectra of samples, different inorganic materials. So you will get a feeling of what is solid state NMR and how it is different from the solution state NMR. So prior to that, just to refresh your memory, I thought I will mention one important aspect, that is the interactions present in the solid state. This we have repeatedly telling in the last two lectures. The first one is nothing but the dipole-dipole interaction. Second one is nothing but the chemical shift interaction. And the third one is nothing but the quadrupolar interaction. Quadrupolar interaction is valid only for nuclei with spin greater than half. That we will come little later, maybe after 2-3 lectures. But the two main, among the three main interactions, the two main interactions we will discuss. The first one is the dipole-dipole interaction, which is having two multiple terminologies, multiple terms contributing to that A term, B term, C term, etc. Out of that, A and B term only are quite important. And among them, homonuclear spin means only A term only will be there. So these things we have already discussed. And then now another important aspect is that both these interactions have an angular dependence of 3 cos squared theta minus 1 or 1 minus 3 cos squared theta minus 1. Oh, no, sorry, 1 minus 3 cos squared theta or 3 cos squared theta minus 1. This aspect we have discussed in the last class. Then we also just mentioned that if I take just without spinning, if I take NMR, I get line shapes like this. This was discussed in the last class. So this broad NMR sometimes will be a little bit disturbing or little bit difficult to explain, but we can get some valuable informations. What happens when you have a variety of environment? This type of many line shapes will join to form a featureless line shapes. So once you get a featureless line shape, it is very difficult to interpret. So if you are having a only single component, it is easy to interpret. So then with that in idea, people thought of thinking about spinning the sample or rotating the sample. Rotation is not a small speed at high speeds, because in solution we go for how much, maybe around 10 hertz, 20 hertz, etc. Whereas in solids we go for kilohertz, not even megahertz. Megahertz is difficult, but at least kilohertz we go. For example, in the spectrum which we are shown here, it has gone up to 1 megahertz. You can see the significant line narrowing. So once you get narrow lines, people will be happy, or system, it will be easy to interpret. So from this only the concept of magic angle spinning came. Now let us discuss what is magic angle spinning. This is a very important aspect, this magic angle spinning. So essentially what is magic angle spinning? Magic angle spinning is taking a powder sample, not a single crystal, because most of the time we encounter powder samples only. Taking a powder samples, put it in a proper rotor. Why proper rotor? Because we are spinning at a speed, so the rotor has to be quite strong. So a rotor has to be quite strong. So we take a good quality rotor, or it's a cylinder. It's a rotor is nothing but a small cylinder. We put the powder in that and then tap or close with the help of lid at both the ends. You know, we are studying with powder samples. So powder samples will have all sorts of orientation, random orientation. We have, suppose we have a vector like this, we have a vector like this one, we have a vector like this one, we have a vector like this one. All sort of random orientation possible. These are nothing but the bond vectors. Correct? Na? One spin is here, another spin is there. For example, if you take like sodium chloride, sodium and chlorine. One entity is sodium, another entity is chlorine. Similarly, for anything, if you take boron oxide, one entity is boron, one entity is oxygen. Similarly, once you take silicon oxygen, SiO2, one entity is silicon and one entity is oxygen. So we have all sorts of orientation possible in the case of a powder sample. It's randomly oriented, nobody can prevent it. Nobody can prevent or nobody have a preferential orientation. So a powder material is there in that cylinder. And then I keep at an angle of 54.74 degree. So what will happen? If I keep at an angle of 54.4 degree, you have the green line shows the actual line which is passing through the sample, middle of the rotor. So if you consider powder samples or grains or particles, you can say the various random orientations as indicated by the green line. I see here I am indicating the green line. See, these are all bond vectors which are randomly oriented. Some are here, some are here, some are the other way. Now what happened? You are rotating. See, there is an arrow given here. See, there is an arrow. I am putting it here. This arrow means I am rotating the sample. Either you can rotate clockwise or anti-clockwise, it doesn't matter. So once you rotate, what happens? Any bond vector, if you rotate it, it will generate a horizontal component also and vertical component also. Correct? Now that is what's shown here. So anything which is rotating will generate a horizontal component and generate a vertical component. Horizontal component will be like this. Vertical component will be, sorry, I am not writing properly, but this is a vertical component and this is a horizontal component. So if you do it fast, what will happen? The vertical component will generate a circle perpendicular to the rod or perpendicular to that green line. And this, since it is generating a rod, it's a circle, it will cancel. Average effect will be 0. Whereas the horizontal component get added together along the axis. So as a result of this, you can generate alignment of the bond vector along the green line axis. So what we have achieved one thing in which the randomly oriented bond vectors mentioned as A, B, BC. BC I have not mentioned. Let us say this is BC, this is B, and this is C. So randomly oriented bond vector. All of them, if you rotate fast along an axis, the horizontal component will align along the green line and the vertical component will cancel each other. So what is the meaning of saying horizontal component will align along the axis and the vertical component will cancel each other? You can see from this figure. In this figure, what will happen? All the bond vector will be aligned along the green line axis so that by rotating at very high speed, you can align all the bond vector at an angle 54.74 degree, 74 degree. For example, a situation like this will come. Let me quickly go through and then tell you. See, initially I have shown. Sorry, I have to. This type of situation will come. You see here this I1, I2. If you rotate it at very fast, all the AB bond vectors or BC bond vectors or all the randomly oriented bond vectors will align at an angle theta, and now the angle theta is nothing but 54.4 degrees. So let me go quickly back to the slide. So all of them will align along the green color axis or at an angle of 54.74 degree. Once it aligns at 54.7 degree, what will happen? Theta become cos squared theta. Cos squared 54.74 degree, that will become 1 by 3, and 3 into 1 by 3 will become 1, and that will be a very small number. So that way you are mechanically averaging out the dipole-dipole interaction. Since chemical shift is also having a 3 cos squared theta minus 1 dependent, it also get partially averaged out. Why partially? Because there are other angular terms also there in the chemical shielding interaction. So due to these other angles present, it may not get completely averaged out, but there is an averaging out happens. Okay, so that way you can mechanically achieve all the bond vector at an angle of 54.74 degree, and this drastically reduces the dipole-dipole interaction and chemical shift interaction partially, and also the quadrupolar interaction, which we have not discussed, but that also has the whole 3 cos squared theta minus 1 as one in one of the terms. So that also gets reduced. Now I have taken from one of the slides which is available in the internet. I think this belongs to Professor Madhu from TFR. So this is a glycine. If you take a C31 NMR of glycine powder, and if you take a static glycine having how many carbon atoms? we all know glycine is having two carbon atoms. One is carbonyl carbon, another is CH2, methyl group. CH2 group. One is CH2 group and another is C double bond group. This C double bond group is a planar structure, correct? Now it is a sp2, planar structure, whereas CH2 is nothing but an sp3 hybridization. So sp3 hybridization normally will be what? Tetrahedral, it is having symmetry. Normally, such species will generate a relatively sharp line. Whereas sp2 carbon is what? sp2 carbon is less symmetry. Asymmetry is the environment, and as a result of this, you generate a broad peak. So that is why if you take a simple static NMR of glycine, you can see two types of spectra. One is a very broad peak and another is a relatively sharp peak actually. Now, if you rotate, if you take this sample as I mentioned, you put it in a powder, it's a powder sample. This is nothing but a powder sample only. And in this line shape, you can get meaningful information from here, sigma 1, sigma 2, sigma 3, etc. of this carbonyl carbon. Whereas here also you will be able to get, but there will be some uncertainty in determining the sigma 1, sigma 2, etc. Because these are all broad line shapes first of all, and we will not be able to very critically say where is the peak maxima because they are overlapping peaks. But if you do magic angle spinning at a spinning speed of 14 kilohertz, then what you get is a relatively sharp lines. You see here a peak here, and you see here is a peak here. The line widths are of course comparable to that of solution NMR. May not be exactly, it will be always larger than solution NMR because one cannot completely average out the interaction. So from this probably you might have got an idea that how the magic angle spinning NMR helps to get information regarding the local environment or the chemical environment. Because if you get a pattern like this now, we can very well say, okay, this proton is something to do with the CH2 group. So it is something attached to the nitrogen, etc. We can get some idea. Similarly, this peak, which is seen at around 175 or 180, is characteristic of the C double bond group. So this also probably from the solution NMR also, exactly chemical shifts will not match solution NMR and solid state NMR. There will be some shift. But from the pattern, you will be able to get an idea, okay, this is carbonyl carbon and this is nothing but the methyl carbon. Hope this is clear too. Now, before going to this one, I will just show you this one. Now, this slide also I have taken from same glycine molecule only. Now, what happened? Here it is static and here it is rotated at a spinning frequency of 14 kilohertz. You get relatively sharp line. There is a small peak here, we don't know what it is. But two peaks are seen, which are characteristic of this methyl group and its characteristic of C double bond. Now, let us go to the situation wherein we can see as a function of spinning frequency, if you do, what will happen. So here what happened, I have done static sample, static NMR pattern is shown here. We can see the C double bond and CH2. Now you rotate it at different speed. You see here I am rotating around 1.181 kilohertz or 1181 hertz. Then I increase the frequency to 3 kilohertz. Then I increase the frequency to 5 kilohertz. Then I again increase the frequencies to 8 kilohertz. So there are some changes we see, is it not? There are definite changes. Some additional peaks are coming. In the case of 181 hertz rotational frequency, we see a large number of peaks. Whereas as you increase the frequency, the number of peaks decreases in intensity. In number of peaks also decreases, intensity also decreases. So these peaks are called side bands. And there is an isotropic peak also there, which is at this position, which doesn't change. But these peaks, this one, these are all called side bands. We will discuss a little bit after some time that how the side bands comes. Similarly, if you see here also, now there is a big peak we are seeing, and both the sides of the big, more intense peak, we see symmetric peaks. You see this peak, correct? Now this peak, and similarly this peak, this peak. So if you measure the ppm here, because ppm is given on the x-axis, and convert it to frequency, you can convert to ppm to frequency if you know the operating frequency. And if you take the difference between this peak maxima and this peak maxima, what you will get is nothing but the spinning frequency. Same thing is valid here. If you take the difference in the frequency here, and if you take a difference of these two peaks, peak maxima, what you will get is a 3 kilohertz. So the side bands are separated at a frequency of from the isotropic peak at a spinning frequency. So if you use 3 kilohertz, the sideband will be separated from the isotropic peak by 3 kilohertz. If you take 5, it will be separated by 5. For example, this is the isotropic peak and this is the sideband. This is the sideband because you see symmetrically separated. So one can easily find out if you know the chemical shift value and then convert into frequency and take the difference, and we can say it is a sideband. If it matches with 5 kilohertz, then definitely it is a sideband. It is not a genuine signal. And another way is also there. When you do experiment, you do at 5 kilohertz also and 3 kilohertz also. Then what happens if the positions are remaining same? Then it's a genuine peak and it's an isotropic peak. It is characteristic of the sample. If peaks are shifting, for example, this peak and this peak is shifting. So this peak and this peak is shifting. So that means they are not genuine peak and they are side bands. They are not characteristic of the nuclei. So this is nothing but the CO group peak and this is nothing but the CH2. Now, if you do at 8 kilohertz, what happened? You see here, the side bands are separated further. Side bands are separated further. Similarly, this also peak is having and one more thing you may note here, this peak is having lot of side bands. For example, the CO peak. Whereas this peak side bands are relatively less. You see here, the C double bond group is spread, the side bands are spread over from almost like 250 to almost like 100. Whereas here the side bands are spread over between a very small value. So this also says the carbonyl carbon is more anisotropic in solid state. Of course, in solution also like that, where compared to CH2. So you see this peak here. It is at 8 kilohertz. Now if you do 10 kilohertz, what happens? This should be further separated. And if you do again 12, it will be further separated. So that is why we see a small peak there. This must be coming from the side band of this one actually. So this is not a genuine peak. Only genuine peaks are these two peaks. You may think that by going higher and higher frequency, rotational frequency, you can get better and better spectrum. You can get high resolution spectrum. You can get more chemical information, etc. It is true. Definitely, we can get the chemical environment or understand the chemical environment by going to higher spinning speed. But one thing we are losing here is that the anisotropy parameters, like whatever we say, sigma 11, sigma 22, sigma 33, are losing because if you use 8 kilohertz or 10 kilohertz, the sideband intensities are very small. So we will not be able to say anything about the chemical shift anisotropy parameters. Because why people go for chemical shift anisotropy parameter? Because in solution, the effect is averaging out. Only in solid, we can get the actual environment around the nucleus. So this information is lost by doing magic angle spinning NMR. But the gain is what? The gain is nothing but the chemical environment. Because if you take this is a simplest molecule glycine. If you take a very big protein or if you take a very big biomolecule, then what will happen? There will be so many CO groups or CH2 groups, NH group, etc., CH groups, etc. So they are all overlapping actually. They will all overlap. So there the chemical information will be preferable. We require more chemical information. So one has to trade-off is there. If you want more chemical information, probably the structural information such as environment, chemical shift, anisotropy, etc., you need to forget about that. Otherwise, if you want more about the chemical shift environment or the distribution of the charge density, etc., we need to little bit play with the chemical environment. We have to record the NMR at a reduced spinning speeds. Nowadays, programs are available, simple programs are available from the intensity of the sideband, we can calculate what will be the approximate chemical shift parameter. That is nothing but the sigma 11, sigma 22, sigma 33, sigma isotropic, etc. So how it changes as the molecule changes, all those things can be monitored by using this software also, by analyzing these sideband patterns. We will not be going into the detail because paper programs are available for evaluating those parameters. So I somehow skipped this. This is to show the advantage of magic angle spinning NMR. Because of course it is very much clear by going for doing magic angle spinning NMR, you can get a lot of chemical information, you can get high resolution NMR, and you can get the information regarding the local environment. But at the expense of this components, chemical shift components of the chemical shift anisotropy. And also, if you see the dipole-dipole interaction also, you lost We may not be able to get anything regarding the carbon-hydrogen distance or carbon-carbon distance from the high-resolution NMR spectrum. We get, of course, we'll get local environments. That is an important aspect. So if you go to very high spinning speed like 25, 30, etc., then we will not get any sidebands, and we can correlate all the peaks with the local environment. So this is one example which shows the powerfulness of this magical spinning NMR. You see here bottom sample, top sample, let us discuss. Top sample is a broad spectrum. You see here nothing can be inferred from that. It's a broad spectrum with some features here. What is happening, we do not know. It's a static stationary sample. The molecule is nothing but potassium arsenic fluoride. It's a powder sample, potassium arsenic fluoride. Here we have recorded the fluorine 19 NMR. Fluorine 19 NMR is a spin half nucleus. But arsenic is nothing but a nuclei with a spin greater than half. That is nothing but 3/2. Both are nearly 100% abundant. So this arsenic electronic distribution will be asymmetric in nature, not a spherical shape. So this arsenic can couple with this one. So that is why we get a multiple, almost 4-line pattern actually. So from this you can get what is the coupling constant and all those things. So this was read at a frequency of 5.5 kilohertz. Even at 5 kilohertz, which is 5 kilohertz is a very low frequency, you can get a beautiful spectrum, and we can get information regarding fluorine as well as arsenic coupling.
Sudarshan?
Yes, sir.
This are you using the proton decoupled or this is a proton decoupled one? Or?
This is proton decoupling. Proton decoupling aspect I will explain later.
But that's why you are not seeing the coupling.
Coupling. Yes. This is a proton decoupling. We are doing a broadband decoupler to irradiate the protons, and then we are doing it. So otherwise,
any references you are using? Or
this has been taken from one lecture given by Professor P.K. Madhu from TFR. So he has.
Normally, how this is, because you are recording a carbon-13 NMR solid state. How you reference the spectrum? Can you put any reference compound?
Yes. We can put reference tetramethylsilane. We can put.
So
solid also we can put a drop along with the pouch. Along with that molecule, that vapor, that drop will be there.
Okay.
It will be like a wet to slightly, sample will be slightly wet, but doesn't matter. That way we can put. Otherwise, with respect to acetone also we can put actually. Methyl group is there. With respect to TMR.
So anything you can put?
Yeah. Anything we can put as a solution.
Anything you can refer that.
Correct.
So you can compare with the solid state.
Yes, solution state actually.
Okay.
This decoupling part I will come with respect to that cross polarization, but for this only just for under. So this also again same only. So this is nothing but 119 NMR. So this also effect is same only as a function of spinning frequency. We get information regarding the sharp lines we get, and these sharp lines can give information regarding the local environment, but we get the information from the sideband. So information is same only we will get by this. This slide also conveys the same meaning. So this has recorded in our, I think in our lab also, this type of compounds have been prepared and we have recorded. So this is a tin NMR, 119 tin NMR, tin having two isotopes. One is 118 and another is 119, 119 and 118. This 119 isotope is NMR active, which is spin half nucleus. So here also we use decoupling, but I will tell you a little bit later. But we probe tin NMR from these compounds. This is an organometallic compound, and we can see as the static pattern is quite broad. The moment you increase the spinning speed, you get sharp lines, and this is the isotropic peak. Sometimes it will be so misleading that the isotropic peak intensity is smaller than that of the sideband intensity. And if you keep on increasing the spinning speed, what happens? This peak only will come up, and this is nothing but the isotropic peak. So from that, by changing in the substituents, etc., some people were working on that. So we get a change in the chemical environment, and we correlate with what is happening with the chemical environment by according to tin-19 NMR. Because some of the compounds are not soluble in solution. Because certain compound, why normally if you have a solution NMR and solid NMR, people first try for solid solution NMR, particularly chemists. Because by putting it in solution NMR, we get rid of these interactions. I should not say unwanted. We get rid of the interactions such as dipole, quadrupolar, and chemical shift interaction, and we can get a local environment information or the chemical information. But certain compounds like glass, certain inorganic solid, some of the organometallic complexes of many group elements, it will be difficult to dissolve in solvents. So in such cases, the only way is to perform a solid state NMR and get information regarding the local environment. Similarly, this NMR has been recorded in our lab, whereas we show tin oxide, we take pure tin oxide. Pure tin oxide is highly crystalline. That is called a cassiterite structure. Probably some of you might have heard cassiterite is an ore of tin. In that cassiterite structure, what happened? We have a tetragonal, it's a tetragonal structure. In the tetragonal structure, you have a tin at the center. You have a tin at the center. This is the blue color is nothing but the tin. And we have octahedral coordination, distorted octahedral coordination. 1, 2, 3, 4, 5, 6. 6 oxygens or atoms are there. So tin is having an octahedral configuration. If tin is surrounded by 6 oxygen, then we should get a chemical shift around -605. These are very qualitative way of interpreting 6 tin, hexa-coordinated tin with 6 oxygen as near neighbor is characterized by a peak at -604. But matter doesn't end there. In addition to that, the next near neighbor like is tin 1, 2, 3, 4, 4 above, 4 below, and 1 just above that as an apex oxygen, apex tin, and this is another below tin, below plane and the above plane if you consider. So if you see here, one tin is having 6 oxygen as near neighbors and 10 tin, 4 from this plane, bottom basal plane, top basal plane if you consider this, or this can be a top and this can be bottom or vice versa. So from this plane, there is 1 oxygen, a tin. So this is contributing to 5 and this is contributing to 5. So there are total 10 tin as near neighbors. So 1 tin is having 6 oxygen as near neighbors and 10 tin as next nearest neighbors. For such a configuration, you can get a chemical shift 604 ppm, and you can also generate the components of chemical shift, which is chemical shift anisotropy parameter like sigma 11, sigma 22, sigma 33 from this by fitting this pattern. So why I am showing this? The moment you dope or the moment you replace part of the tin with titanium or any other metal, then there is a change in the line shape, chemical shift, etc. And this also affects the local environment. It has changed from an octahedral, nearly octahedral, to more and more distorted environment. This, in fact, you can visualize with the help of the tin 119 mass NMR. In fact, one problem maybe the next class or next to next class, maybe that I will give as an assignment. A similar problem I will solve in the class. And the problem on this tin oxide, I will give as an assignment, maybe in the 6th lecture. Today is 3rd, maybe in the 5th lecture I will. So probably this you might have understood by this time. By doing mass NMR, you can generate a very narrow line shape, and the side bands which are getting generated can be removed by going into higher and higher spinning speeds. But remember that going to higher and higher spinning speeds is difficult because we should have a mechanical system for that. So many times we encounter problems while going for higher and higher spinning speeds. This, I think, a similar spectrum I have shown for mercury sample last time also in the last class also. You see here, this is the static spectrum. We can get easily information regarding the chemical shift MRC. This is symmetric. Sigma 11 is equal to sigma 22. The chemical shift anisotropy is more symmetric. Previously, if it is asymmetric, means sigma 11 is not same as sigma 22 and sigma 22 is not same as sigma 33. Here, sigma 11 and sigma 22 are same. This is an axially symmetric system, and accordingly, you can see how the sideband pattern also getting generated. Now we have mentioned why sidebands are there. Why sidebands, or what is the mechanism for sideband generation? Why we cannot get rid of these sidebands? Because if you go for a protein molecule or a large molecule, large biomolecule, and if you do spinning, if you do magic angle spinning NMR, what you get is you will get a lot of lines. So very difficult at that stage to say which one is isotropic peak and which one is sideband. You will feel a lot of difficulty, and this will come when you go for higher and higher frequency also. So I think just I will, okay, first before going that, I thought I will, before doing this magic angle spinning NMR, how we will do a magic angle spinning NMR? We have a rotors like this. This is nothing but made of zirconium oxide, ZrO2, zirconium oxide. This zirconium oxide is a very stable and very robust. It doesn't get break immediately. So then we have a polymer called KLF. And two units are there. One is this zirconium oxide rotor, You can see this is called a rotor because it is like a cylinder. And then we have a cap. This cap is made up of a polymer. So by using suitable small equipments are there in which you can remove this top part from this bottom part, and then you can fill the powder. Because we are now all these studies which all the experimental results which I will be showing is of this only, so powder samples only. We never work on single crystal materials. So we are all discussing on powder samples. So you have a rotor like this one, and you see there is a black line. You see here, half of the bottom is covered with the black line. Why this black line is there? Because if you are rotating at very high speed, if there is no black line, or if there is, the detector cannot distinguish, because detector is nothing but a laser only. Laser beam will go and come back. So if there is a black thing there, laser beam will not get reflected. If there is a white beam, laser will get reflected. So that way one can monitor the spinning frequency. For that only that black line is there. Now, as I mentioned, see this is the coil. Coil is only one coil only is there. It's all solid state NMR, of course. Most of the solid state NMR which we study, one coil only is there because the decoupling and the signal pulse is given through single coil only. So here we put the rotor containing sample. This is called a rotor and this is called a cap, and inside open the cap and we'll the powder, and this will be kept at an angle 54.7 degree. That is the magic angle. This will be rotated at very, very high speed. This is nothing but the coil, or we can say RF, radio frequency solenoid, which is used to give the radio frequency pulses. So I thought one more photo I will show. See, if you are going for 10 or 15 gets, we can use, for example, this is a bigger one. This is actually 7 mm rotor. So if you are using this one, you can go to only up to 5 kilohertz. So previously 10 years or 15 years back, we can go only up to 5 kilohertz. For example, the pattern which I have recorded here, for example, you see here it is rotated at maximum 5 kilohertz. We cannot go above 5 kilohertz. Because with this much big rotor, we cannot go to very high spinning speeds. But if you go to smaller one, you see here 4 mm rotor. If you have 4 mm is diameter of this one. If you open the cap and measure the diameter, it will be around 4 mm. If you have a 4 mm cap, 4 mm rotor, we can go up to 15 kilohertz. Very high spinning speed we can go. But one more thing we are forgetting, once you reduce the size, then what happens? Sample quantity also will reduce. So once sample quantity reduces, you have to run for long acquisition times. And another is 2.5. 2.5 if you see, you see here very small one. Of course, it can go up to 35 kilohertz, and the smallest one so far, I think I know only up to this much, is 1.3 mm. So which can go up to 60 kilohertz. 60 kilohertz means it will be really challenging rotating the sample at 60 kilohertz because a lot of mechanical inputs and then air pressure, etc. is required. So then temperature also, if you go to very high speed, then what happens? Temperature also can change. So all those things we have to take into consideration. So this cap is a very, very important, because while spinning, if the cap opens, then again the problem will come. We will not be able to do any. So I thought I will just show one more slide and then we'll go to the technical aspect. Normally, this is what called a boron nitride actually. So boron nitride caps are there. A stator, this is called a stator. In the stator, there is a hole you can see. There only this coil is put. Actually, when we were trying some experiment, the coil got broken. So we have taken out the coil and took the photograph of that. So this is the coil. This connection you see here got broken because probe got opened there, sample got opened there, and then it got broken. So the coil got broken. Actually, there is a coil. It's a perfect coil. So this I am showing a broken coil just for a feeling of that. So this is going inside, and the stator is kept here. So this is nothing but made up of machinable boron nitride. That is why whenever we record boron NMR from solids, we need to subtract the background, because invariably all spectrometer we have the boron, because it is a machinable also. It is quite strong also. Its mechanical strength is quite high. Even if you rotate at very high speed, nothing happens to this one. So that is why when we do, particularly in borosilicate glasses, we do boron NMR. First of all, we do is first record the background. How does it come? And then subtract the background from the sample. So that we will get the sample response. So this is something to adjust the magic angle. This is the vernier, you can see here. So vernier is used to adjust this stator, because inside the stator there is a coil. So this vernier is adjusted to adjust the angle, and by you can vary the angle. Sometimes people do off magic angle experiments also. Of course, the line width will be broader, but sometimes people do that actually. So for that purpose, we can change the angle also by this vernier. So now, so far it is clear, you understood there is a rotor is there, we put the sample inside the rotor and rotate it at very high speed, and then we get rotating side bands, and the side bands can be distinguished by changing the rotating speed. You see here, when I am changing the rotating speed, side bands position is changing, whereas isotropic peak position remaining same. So we can, by varying in the spinning speed, we can get information regarding the isotropic, which is isotropic peak and which is the genuine peak, which is the side bands. Now let us see how these side bands are coming. Correct? Now it is very, very important aspect, and how they are disappearing when you go into higher and higher spinning speed. This lower and lower spinning speed only, the side bands are there. If you go to higher and higher, I think in the first slide today in the beginning I have told, if you go to 14 kilohertz or 15 kilohertz, you can get a negligible side bands, very, very poor or low intensity side bands. How it is happening? So I just to give a picture, you try to understand this, how we will get a reduced sideband intensity. See here, first rotor I am showing here. Rotor is at this position. Now, rotor has changed 180 degree, 270 degree, and again come back to the same position. Correct? Na? Half a rotation is completed here, and one full rotation is completed here. So what must be happening when I am rotating like this? One half rotation and then one full rotation. Full rotation means I have started from here and I've gone through all these positions and come back to the same position. So initially when this rotor is at this position, there are various spin packets. I should say the powder samples contains a lot of grains or spin packets. So all the spin packets will have some frequency, it will be felt at this position. But now what happened? You are disturbing the system. You are rotating it. First a half rotation and then a full rotation. So by doing this rotation, what happened? Whatever the spin packets which are there inside the powder will feel a range of magnetic field. Is it not? Because at this point it is seeing a particular magnetic field, all the spin packets. And once they feel a magnetic field, it will have a frequency called omega is equal to gamma h0, where omega is nothing but lambda positional frequency and the h0 is nothing but the applied field. But the moment you half rotation here and one complete rotation, then it will generate a range of field. So range of field is like a disturbance, correct? Na? Range of field is like because anything which is a spread, any spread in the magnetic field is like a disturbance only. So what happened? It will feel a range of field. And finally, it will come back to the original position like this one. Correct. So first you start from here and then you rotate half circle if you complete and you rotate and complete. So you will see a range of field, and this range of field is like a disturbance. So it will have a range of magnetic field felt. So it will have this type of response, and then finally it will come back to this type of response again. So this is nothing but the FID. So FID normally it will be like this. Whatever I have the upper line, if you see, a continuous line is not normal FID if you give a static sample. But if you're rotating it, you are doing some sort of a disturbance now. So FID changes like this and again come back to its position. Again, you are getting one more circle. Again, it changes and come back to its position. A situation can be similar to that of some sort of an echo you can generate. Correct? Na? See, the magnetization comes here first. Then there are some disturbances in the spread in the magnetic field. So magnetization comes back. There is some disturbance, they spread it. But again, it has come back to the original magnetic field. So again, they undergo refocusing. So this is without applying any false due to rotation it is happening. So that is why this is generally leading to this type of sideband patterns. So once you rotate faster and faster, what will happen? The time period, this is one time period, this is half time period and this is full time period. This full time period will keep on decreasing. Correct? Na? So full time period, once it keep on decreasing, what happens? The sideband gets farther and farther because this is whatever happens in time domain, the reverse will happen in the frequency domain. If the time domain is decreasing, it is the frequency domain, it will increase. So what you will get is the whatever you are coming here will decrease its frequency. the period will decrease. Once the period decreasing, it will get separated and separated. So this is the origin. Actually, this is the simplest way of explaining the origin of course, quantum mechanically also people explain, which I am not going to discuss here. If you are interested, such books are there. But this is the way in which a simplest explanation given to the sidebands, the origin or the generation of sidebands. So this is a similar type of thing, spin echo sequence. We will study, probably you might have studied in the solution NMR, how to generate spin echoes and get the, because many times dead type problems are solved with the help of a spin echoes only, dead type problems. Here we use a 90-degree pulse and then a pi/2 pulse, and then you generate an echo. So this echo is used to solve dead time problems in NMR. So this probably we will discuss it a little bit later, but this is somewhat similar, this rotational echo. This echo is coming because of the rotation, so we call it as a rotational echo, and the rotational echo is responsible for the origin of sidebands in mass NMR. Hope this is very clear to everybody. If anybody is having doubt, please mail to me, we can discuss. This is an important aspect in mass NMR. So now, as I mentioned, we do not know any sample. Before doing any experiment, we do not know magic angle, which is the magic angle, with the help, because we don't know the magnetic field direction. Of course, we had a rough idea, but we will not be able to keep a exact, accurate magic angle. So determination of accurate magic angle is an important aspect. Without knowing that, we will not be able to do a mass NMR. So normally, they take a variety of nucleus, like lead, sometimes carbon-13 also they take, and then normally ideal nucleus which people use is bromine 79, which is a spin half nucleus, which is a which is a spin 3/2 nucleus, which is a quadrupolar nucleus. So this quadrupolar nucleus, there is a disturbance, or there is a non-uniformity in the charge distribution. There are multiple transitions are there, plus half to minus half, minus half to minus 3/2, etc. Plus half to plus 3/2 to plus half, then plus half to minus half, and then minus half to minus 3/2. One central transition and two satellite transitions are there. So this another advantage is that KBR powders are high purity KBR powders are available in IR spectroscopy, and sometimes Raman also people use. IR spectroscopy people mainly use high pure KBR powder. So that way it is purely available. And also bromine in KBR. Bromine is having only one environment, like sodium chloride is having only chloride ion is having only one environment, which is nothing but octahedral environment. Each chlorine is surrounded by 6 sodium ion. Similarly, in KBR, each bromine is surrounded by 6 potassium ions. So we have a octahedral symmetry first of all, and we have pure material. And then if you see one signal only is there, that is also advantage. So we can monitor the sideband patterns as a function of spinning frequency. So if you want to set the magic angle, you take powder KBR, pack it inside a rotor, and rotate at a very high spinning speed, maybe at 1,000 hertz, means 1 kilohertz or 2 kilohertz. And if you see sufficiently narrow sideband patterns, then we can say this is a proper magic angle. If the sidebands are weak in indents, if the sidebands are relatively broad, then we say we are off magic angle. We are away from the magic angle. We need to adjust the vernier in such a way that we need to get sharp sidebands. And sharp sidebands are indication of the actual, means the correct magic angle. So you can see, if you keep at the magic angle, you see there is a broad FID which is falling down, and along with that FID, you see lot of rotational echoes. This has been recorded in our laboratory only. You see the echo signals you can see. If you can get lot of echoes in FID, then you are sure that you are close to the magic angle. You are very, very close to the magic angle. Then only you can generate these sharp lines are nothing but echoes. And you say a broad FID decay. But if you are away from the magic angle, you see FID, but you see the number of rotational echoes will be smaller. So generation of effective rotational echoes is very much required to get a magic angle condition. This is of course is an experimental aspect, but I thought it worth mentioning whenever you do. Sometimes what happens if you are not at the magic angle, you get unnecessary broadening in the line shape, and you will be trying to interpret that based on the changes in the chemical environment or changes in the asymmetry parameter, etc. So to make sure that we need, first of all, we have to make sure to delineate that aspect. we need to make sure that the sample is at the magic angle. So this experiment, it won't take much time. Any recording, before recording any solid state NMR, we first record this and see, of course, whether the sample is at the magic angle or not. Hope this aspect is clear to you. Then one small thing I wanted to tell is that this Fourier transform, as I have mentioned, it's an inverse transform. If the pattern is, if the decay is quite fast, FID is nothing but the free induction decay, there is no pulse here. So the decay is very fast, then the change in the line shape, the line width will be broad. If the decay is somewhat slower, then we get sharp line shape. This peaks which we have seen overlapping, which is superimposed over the decay, is nothing but the rotational echoes. Let us explain, let us discuss some simple things like how an NMR of a glass will be different from NMR of a crystal. This is nothing but quartz. Quartz you might have encountered many times in the laboratory, because sometimes people use quartz glasswares, or sometimes for quartz tube for heating at high temperature, etc. If you take this quartz powder SiO2 crystal, even though I have written crystal, it is not a single crystal, it's a powder sample. So if you take an SiO2 crystal and powder it and record a silicon 29 mass NMR, this mass stands for magic angle spinning, and 29 Si is the isotope of silicon. Silicon is having two stable isotope. Of course, I think other isotopes are also there. One is 28, which is the highly abundant, and 29, the silicon is less abundant. And silicon is also a unique nucleus with the gyromagnetic ratio negative gyromagnetic ratio. So getting silicon NMR is difficult, record NMR, because the moment gamma is higher, it is better to get good NMR patterns. As the gamma decreases, the sensitivity decreases. So silicon is having a poor sensitivity. So you can see the line width, you see when the same material only, here the silicon is tetrahedrally coordinated, here also silicon is tetrahedrally coordinated. But in one case, you see the line width is of the order of 3-4 ppm only. ppm you can see here, because this is -100 and this is -1 time. With respect to tetramethylsilane, you can say tetramethylsilane is the reference compound, which you can put a drop in the powder and we can record the spectrum. So here, SiO2 glass, you see how much very difficult to get a good quality spectrum. You see how much noise it is, lot of noisy, but you are getting a pattern here. So this also quite broad. Why this broadness comes? Whereas in crystal, there is sharp lines. Why this broadness comes in the case of a glass? Because in the case of a glass, at bond lengths and bond angles are not well defined. For example, in the case of a SiO2 crystal, there is a fixed bond length and fixed bond angle. So there is a symmetry. Once there is a symmetry, then we will get very narrow line shape. In the case of a glass, there is a distribution in the bond angles and bond length. For example, here it is, let us say it is 109 degree, but here we have a bond angle variation from almost 102 to almost like 150. Accordingly, bond length also varies, so you get a broad line shape. So from the line shape itself, the spinning speed was around 10 kilohertz. If the line, from the line shape itself, you can say, of course, this is an amorphous material and this is a crystalline materials. Of course, we need not do NMR for this. Of course, X-ray diffraction patterns are available, but you can get information regarding this by NMR also. Since I have shown NMR of the crystal as well as glass, I am also showing the XRD pattern. You see here, borosilicate glass or a silicate glass is having somewhat similar to that, and XRD pattern is something similar. It's a broad, which is same for silicate glass also, borosilicate glass also nearly same. So you get a broad peak, whereas SiO2 crystal, you get a sharp peak. But one thing is there, even you get a broad peak, the peak here shows the silicon is tetrahedrally coordinated, because it is coming around -110 or -112, indicating that even in this glass, silicon is having a environment which is distorted, but it is a tetrahedral environment. Of course, I will show you some examples in which octahedrally coordinated silicon, how does it look like. But this information means this is nothing but the short range order in the glass we can get by recording the NMR pattern of the glass. So this anyway I have discussed. Then normally what will happen, the silicon NMR, we will not do only silicon NMR alone, because we have programs also for making different types of glasses. So different types of glasses have various applications, which we will discuss it a little bit later, maybe probably on the next class, because we need to modify the glass properties. We make to toughen the glass. Many times in the glass buildings, we have glass windows. We need to have a very toughened glass. then we have to have a glass windows for various other applications. And glass also we are using for various optical applications like band pass filters, but narrow band pass filters, then cutoff filters, a lot of notch filters, etc. So these things also we need to take a glass and modify its properties. Modify its properties means what we have to do? We need to modify the structural unit. Then only we will be able to modify the glass properties. So what is the basic structural unit present? Basic structural unit present is a silica tetrahedra. So normally silica tetrahedra basic structural units are represented by Q4. Why Q4? Because 1, 2, 3, 4. 4 bridging oxygen atoms are there. A silicon is surrounded by 4 bridging oxygen atoms. So that is called a Q4 structural unit. So Q4 structural unit, as I mentioned, it is having a chemical strength value. It is well established that it is around in crystalline silicates also it comes around minus 110 ppm. This minus 1. This is a very qualitative way, but still we can identify in the glass that there is a silicon structural unit with 4 bridging oxygen atoms. Now if you add sodium, what happens? Sodium has to be accommodated in the glass because glass is a homogeneous matrix unless a crystalline material. So how to sodium oxide will be accommodated in the glass? It will try to make this bridge, convert the bridging oxygen into non-bridging oxygen. So a bridging oxygen will undergo a scission. In fact, a bond will break here. Bond breaks occurs. So once the bond breaks occurs, what happens? Because here already it is silicon. SiO, correct now? SiO. Once the bond gets broken here, one O minus generated here and one silicon plus generated here. So O minus will be neutralized by one of the sodium in Na2O and the silicon plus will be replaced by ONA minus. So you generated, by putting one molecule of sodium oxide, you generate 2 molecules of Q3 structural units. This is a Q3 structural unit. You see here Q3 structural units. So Q3 comes here. So Q3 is nothing but a silicon structural unit with 3 bridging oxygen and 1 non-bridging oxygen atom. So this oxygen non-bridging, this is called a non-bridging oxygen atom, and this is also called a non-bridging oxygen atom, and this is called a bridging oxygen atoms. Why non-bridging oxygen atom we are bothered? The moment you generate a non-bridging oxygen atom, the optical property changed. Why? Because if you have only bridging oxygen atom, then there is no negative charge on oxygen atom. If there is a negative charge coming on the oxygen atom, it is easy to excite that electrons to the higher level because negative charge repulsion is there. If you see the valence band and the band theory of solid, normally negative ion or the oxygen, sulfur, etc. forms the valence band and the metal atoms forms the conduction band. That is generally the concept or generally the approved way of thinking. The metal atom forms the conduction band and the oxygen atom or the negative charged anion forms the valence band. So if you are generating a negative charge on the oxygen, what happens? It is easy to excite that electron to the higher level. So optical gap decreases. So the transparency window of the glass changes. So the transparency window, the onset of absorption can be correlated to the quantity of non-bridging oxygen atom generated in the glass. So this non-bridging oxygen atom concentration can be only obtained by NMR technique. You cannot get any information from XRD because this information is buried in the XRD pattern. But by recording the relative concentration of Q3 and Q4, estimating the relative concentration of Q3 and Q4, you will be able to find out how much non-bridging oxygen atom is there and how much bridging oxygen atom is there. And this decides the optical transparency or the cutoff wavelength of the glass. So glass people use for various purposes. So this purposes, we can, for this purpose, which glass will be suitable for this purpose, we can have a judgment or we can get information regarding this by recording the silicon titanium mass and NMR spectrum. So this is one of the very good information provided by magic angle spinning nuclear magnetic resonance to estimate the relative concentration of the non-bridging oxygen atom. Another important aspect, see, once a bridging oxygen atom gets converted to non-bridging oxygen atom, then what happens? The rigidity of the glass, because here one silicon is pulled by 4 oxygen and this 4 oxygen is also grounded, is pulled by another silicon. But the moment you cut this bond, you are generating a non-bridging oxygen atom, the pulling power or the rigidity of this thing decreases. This rigidity has a direct influence on the thermal expansion coefficient and elasticity of the material. So by estimating the Q4 and Q3 structural unit, we can relatively predict what will happen to the thermal expansion coefficient and what will happen to the elasticity parameter of the glass, etc. So this is a very good information because many times people use for the seals. Glass to metal seals are used for various applications. So that can be predicted by recording the P31 mass NMR. And many times it is not that we will work on glasses, we also work on crystalline material, and we also work on materials which contain both glassy phase also and crystalline phase also, because they have a lot of advantages. So such materials are called glass ceramics. The glass ceramics also we can study very well with the help of NMR, because if you take a lot of amorphous environment, the XRD will not give any pattern, any indication, because the amorphous pattern will generate a broad peak and the sharp peaks will be buried inside that. So if you get a broad peak and superimposed with a sharp peak, then we can say it's a glass ceramic material. So very good information we can get from the glass ceramic material. Why glass ceramic we should study? Because if you take a glass, you see here glass, if you just touch or if you hit, it will become into shatter into pieces. You see here a lot of glass pieces are there. This will create less menace, or this is a problem actually. Similarly, if you try to make a hole, suppose I want to make a window in a glass window, I want to make a hole, the situation you will end up like this. You cannot make a hole because you see glass is a brittle material. So you cannot make a hole into glasses. And now suppose you want to make a hole into glass, what happened? You need to convert the glass into glass ceramics. We have to machine the glass. We have to make a machinable glass. So machinable glass can be possible only by carrying out a proper thermal treatment. So by doing proper thermal treatment, what will happen? We will have a crystalline phases generated. So we have a glassy phase generated, we have a crystalline phase generated. By understanding or by evaluating the relative concentration of the crystalline amount and the relative concentration of the glassy material, you can predict or you can identify or you can have a procedure or you can have guidelines for making a good quality glass ceramics. So this type of people work a lot of people do. From NMR, they get the information regarding the structural unit and percentage of crystalline or a ceramic component, and then try to estimate its thermal expansion coefficient or this machinable character, etc., by recording NMR. So I am just giving one example of how NMR is helpful in finding the machinability of the glass. For example, a glass with this composition, for example, a glass with this around, I think, 10% alumina concentration is giving significantly more amount of a crystalline material called a potassium fluorofolgopite, wherein which silicon is having 5 different environments. You can see 5 peaks here, 1, 2, 3, 4, 5. So this is just what is already there. 1, 2, 3, 4. These 5 peaks are characteristic of the potassium fluorofolgopite phase, which is having a layered structure. The presence of this layered structure is extremely important for predicting the machinability of the glass. So that is why this magnesium glass ceramics we investigated. This is a study which is carried out in ARC only. So this magnesium aluminosilicate glass is very widely used for making machinable glass ceramics. And in that glass ceramic, there is a compound called potassium fluorofolgopite, which is having a tile-like structure. You see, it's like a mica-like structure. Mica is nothing but tiles now. With the help of a cello tape, we can scotch by tape, we can remove the layers. So the same thing you can do to remove the layers, and this is nothing but which gives flexibility to the magnesium aluminosilicate glass, and the NMR is the technique which is used to identify or to evaluate the relative concentration of the magnesium fluorofolgopite phase, and that determines the machinable character of the glass ceramics materials. Yeah, I may stop here. What do you say? So next class we will give some more example wherein which solid state NMR can be used to identify the different structural units present in the glass and how they affect the thermophysical properties or material properties of the material. Please feel free to stop me at any time. I will be ready to interact. I am ready to answer, or if I don't know, I can refer and tell you. But I am ready to interact with you. Please feel free to contact me. So my email ID.
So you can interact in our chat.
Yeah, only. You can email me also, or you can stop me at any time. It will be better if you go in a dialogue manner. rather than a monologue. So at any time you can stop me. This is a discussion time. It's a basic course only. So this is a basic NMR aspect. Basic NMR
दूसरा
aspect.
उसमें वो attendance लेगा इसमें तो है 3 लोग
3 लोग है Okay.
हाँ साइन ये अंकल दुबे और ये तापस रनियर्स 3 लोग आई थिंक लोग
Molla, I think he has attended first class also. Many experimental aspects of NMR I am covering here. So it's over. No? Okay.